I'm Fausto Di Vincenzo, and I joined MSC in 2009 in Rome, and in 2012 I joined the French technical team and the pre-sales team, and I'm really active in everything that concerns fluid structure interaction, aeroelasticity, and so on. As you may know, we have acquired Cradle, that is a leader in the CFD simulation with SCTetra and now with SC And so for this reason, we started working on the code simulation, and now we have put in place two different simulations, able to couple both Nastran and Marc to Cradle CFD solver. So I want to go through the agenda first so that you know what I'm talking about today. So the motivation and the objective of all these activity, and I will go through the coping strategy in order to explain further in detail how the fluid structure interaction simulation works, and especially for Nastran, Marc, and both SC Flow and SCTetra. And I want to also put the attention of something that is really crucial in terms of FSI, that is the Aero-structure interpolation, because these affect the solution, the accuracy, and the quality of the co-simulation. And the other two aspects, that is the performances, that we have been working a lot of this topic in order to improve the performances of the simulation, and some applications that you can appreciate where we have been using this technology. And another important point is the fluid domain morphing, because we know that when we couple an FEM model with a CFD solver, we not only send information from one solver to the other, I mean load from the CFD to the FEM model, and displacement with velocity and acceleration to the CFD solver. But we have also to think about how the CFD domain is morphed. It is really important because as soon as we get negative volume issues, the CFD simulation gets stuck. So we have to avoid this. So we have been working a lot of this topic, and I'm going to explain how everything works. And at the end, I want to perform two different demos. One is with Marc and SCTetra, and the other one is with Nastran and SC Flow, both from Cradle solution. And at the end, as Farnaz said, we can have question answer more. So in terms of motivation and objective, so as soon as we have acquired Cradle, we thought about developing a unified environment able to couple any FEM solver to any CFD solver. So to have something that is really flexible. We wanted also to develop something really efficient, robust, and fast in order to perform an efficient fluid structure interaction simulation. So for this reason that we have been working a lot in terms of performances and reducing memory requirements, and for this we have put in place something really cool in which we have used Nastran to do a lot of stuff. And the other important aspect that I already mentioned is that we implemented interpolation between the structural and the CFD solvers within the same simulation. So the only thing that we need is the CFD solution, the CFD solver, the structural solver, and everything is done automatically. And sorry, but for this reason, so the objective was to develop something that we call hybrid fluid structure interaction tool, hybrid, because it is general. We can apply to any structural and CFD solver. Let's have a look at the coupling strategy. So the HFSI tool is a general interface, and MSC has developed to allow for three-structure interaction simulation. So the CFD and the structural solvers execute simultaneously in a staggered coupling and exchange information through this general interface during the simulation, and this provides a tight coupling between the two codes. The data interpolation, as usual, is done on nodes that belong to the so-called wetted surfaces. And we know, for all of you who worked on this topic, we know that the CFD wetted surface is always different from the structural wetted surface in terms of discretization, in terms of shape. So with the interpolation procedure that we have implemented, we can handle any kind of CFD mesh, poly mesh, divider mesh, and etc., and any kind of structural elements in terms of Nastran, for example. We can use beam, we can use just a bunch of grids, we can use plates and solid, and etc. And the last point is that the fluid domain morphing is performed by the HFSI module as well. So if we look here at this box, so the outer box is the general interface tool. We have mainly three different boxes. So on the right side, we have the CFD solver. On the left side, we have the FEM, and on the center, we have the HFSI Nastran modules that takes care of the interpolation between the two solvers. So if you look at the way we have developed this tool, you can easily understand, and we can easily remove SC flow and put on its place SCTetra or whatever CFD solver we want. This is because the way we have developed it allows us to remove one solver and use another one, and this is thanks to the HFSI Nastran module that I am here aligning here in the center. So how does it work? So this module gets directly CFD forces instead of structural forces, and interpolates these forces to the structural model. It gets directly structural displacement, and it puts displacement, velocity, and acceleration if needed directly on the CFD model. So what we have developed so far is two coupling. So we can couple soft-400 by means of OpenFSI to SC flow and SCTetra, and we can even couple Marc through the code coupling interface to SC flow and SCTetra. So one of the common question I get from customers, so could I use another CFD solver instead of Cradle? I won't be happy, because I would like the customer to enjoy it, to try Cradle, because there are a lot of interesting and amazing stuff on it, and it's really it's fantastic. But if the customer is interested in using their own CFD solver, they can do it. So it needs a little bit of adjustment maybe, but it's easy to remove what we have done here and put another CFD solver. So let's have a look more in details about the soft-400 SC flow and SCTetra coupling. What we have here, as I already said, we have three boxes. On the right side, we have the CFD solver. On the left side, we have Nastran, and on the center, we have the Nastran module needed for the interpolation. We have developed through the API available from Cradle and using user-defined function, and we have done the same for soft-400. We have used the API available from OpenFSI. So how do these two solvers communicate to each other? So the CFD solver creates CFD forces and sends these forces on the Nastran module that, as said, interpolates on the structural solver through the OpenFSI interface that is a specific OpenFSI CAD service that we have developed. So it is not what you find in the installation of Nastran, because it is empty. So you have to develop your own services if you want to connect software with to another external solver. So we have done it. So software understood the connection to the OpenFSI service gets the rapid node forces, solves for the time step, and said rapid node displacement, velocity, and acceleration. These information are got by the interpolation module, and the HFSI Nastran modules send all the displacement and velocity and acceleration of the entire CFD domain to Cradle, I mean to SCFlow or whatever, to SCTetra, and by the AIL move function, we move the CFD domain. If we look at the coupling between Marc and Cradle, it's pretty the same thing, and this is what I said already, that this is thanks to the flexibility of this interface. So if you look at the CFD side, we have the box that is still the same as in the coupling with Nastran. In the middle, we have the same, exactly the same HFSI Nastran module that takes care of the interpolation between the two solvers, move the CFD domain. And on the left side, instead of having SOL 400H OpenFSI, we have Marc, and in this case, we have developed a specific code coupling interface that we have called HFSI, that is an executable, and you can use both in Windows and Linux. And the data exchange between the two codes it's pretty the same thing as before. So the CFD solver sends forces on the CFD wet surfaces. These are interpolated on the structural model. Can be Nastran, as already said, can be Marc, as in this case. Marc solves for the time step and put the displacement of the structural wet surfaces, and the HFSI Nastran module get this information, interpolate on the CFD model, and send all this information to Cradle. And so all the other time step is the same. So through this slide, you can easily understand how it would be easy to replace one block to another, because what does not change is the HFSI Nastran module that takes care of the interpolation between the two solvers. But since we have developed specific function to get CFD forces, to put domain deformation, to put FEM forces, and to get FEM displacement, makes this interface really, really general. And here I want to spend a few words about how we connect, how we tie the CFD to the structural wet surface, because we know that the two meshes are different. So how do we tie them together? So we need only 3 steps. So first of all, we use the spline technology available from Nastran. We import the structural model in pattern, or fidelity, the same thing. We then import the CFD wet surface, and to do it, we have developed a menu that is called HFSI Toolkit. Actually, it is a plugin to slide loads and pattern that we use to handle CFD results. So we import both wet surfaces from Cradle and the other from NAT or from Marc. And we create the spline as the video is showing here. So we have spline 6 and spline 7 available from spline technology. We choose the aerodynamic wetted surface, the structural wetted surface, and an important aspect here is that we define the number here, the number of splines that we want to create. This is really important in terms of accuracy, in terms of memory requirements, in terms of performances. And we show you some application later on during the webinar. So these splines are created. As you can see, there are several splines to tie the two wetted surface together. And as soon as we have done these 3 steps, 3 actions, really simple, we can run from flight loads and from the toolkit as well, a specific Nastran solution, and we punch out a spline OP2 that is binary file that contains the spline interpolation matrix between the 2 wetted surfaces. So this is the spline OP2 is what connects the 2 wetted surfaces together. If we look at the data exchange during the simulation, I get here one time step. So it is pretty the same thing that I have already said and explained, but the difference is that here I have put the spline OP2 in the HFSI Nastran model, because this is what allows us to interpolate information between the 2 wetted surfaces. So we get pressure from the CFD solver, so we get the forces by the module, and by using the spline OP2, we get forces on the structural solver. We solve all the time step, we get back displacement from the structure. We can even use velocity and acceleration, and we have the morphing of the CFD domain. So what the Nastran module sends to the cradle side is the entire CFD domain deformation. So the only thing that the CFD solver needs to do is only to move this node with the information received by Nastran. So it is easy to understand how this interpolation can be used for other software. And I want to spend a few slides to talk about about the Aero-structure spline interpolation, because this is really important for me when we perform FSI, because the quality of the solution really depends, is really affected by the way we perform this interpolation. So let's have a look on how we perform this interpolation by employing the spline technology. As already said, as soon as we import the CFD wetted surface and the structural wetted surface in flight loads, we can create the spline, and running Nastran, we can punch out the spline OP2, that is the spline interpolation matrix that tie together the CFD to the structural model. And as soon as this spline is put in memory in the HFSI Nastran modules, we can interpolate the load from the CFD to the FEM. And what really matters to me is to see that this technology ensures the energy equilibrium when we transfer the load from the CFD solver to the Nastran model or to the Marc model. So in this case, we have a three-dimensional wing model, and if we look at the elements here that are loaded, are only nodes on a beam. So in this case, we use a beam without any problems. And since this technology is based on 6 degrees of freedom, we can transform aerodynamic pressure into an equivalent force and moment vectors, and the energy is conserved. as you can see here in terms of forces and moments. So this is really important. The other important aspect when we send back displacement through the CFD solver, so about the displacement interpolation, we use the same spline technology, the spline OP2 matrix that we have created, and using the same beam model, you can see how the wetted surface deforms smoothly and regularly. And this is really important when we perform co-simulation. Otherwise, the CFD solver can easily diverge, and we have to stop the simulation. So that, in terms of accuracy, is really important, and this is the interpolation procedure implemented in the problem. In terms of performances, if we remember that I've said that the spline OP2 interpolation method is put in memory in the user service in the Nastran model at the initialization phase. First of all, we have to create it as fast as possible. So we have to improve the efficiency of Nastran in order to create it, and we have to reduce the space needed to store this spline. And this is the reason why we use fly load and the HSA tool. For the model that I've just shared, we have something about 60,000 CFD wetted nodes and 40 FEM structural nodes. By employing the HSA toolkit that, as I already said, is a plugin to Tetra, we can reduce the time needed to create a spline from 30 minutes to something like 20 seconds. So we have 50% speed up. And the other important aspect is that if you look at the space required to store this matrix, the size of this matrix goes from 2.2 giga to something like less than half a giga. So this is really important. And the other aspect is if we increase the number of splines that are automatically created by this plugin, and we look at the load distribution that we get after the interpolation on the structure, we are really able to pretty well describe the aerodynamic load on the structure. So it's really detailed. And this is thanks on the way that we create the spline by using fly loads and this plugin. So we improve the performances, we improve the accuracy, and we reduce the time, the size of the spline. Another slide in terms of performances, this is something that I have presented the last IFAS conference in Milan, and we have done an activity with the engineering school here in Toulouse, SEA. We have performed steady-state simulation, FSI, and we have something like 3,200 thousand nodes in terms of the CFD model. And we have coupled this rotating blades system with a beam, Nastran beam model. If we look at the performances in terms of splines and so interpolation of spline, look at the table on the both sides. So we have studied something like more or less 9 configuration, and we looked at the size of the spline matrix and the runtime taken by Nastran to pay this spline. So we went from something like 12 giga to something that is really 0.2 giga when we employed about 300 splines. So the splines here are automatically created by the plugin, so we don't have to take care of it. So the tool takes care. So we only need to use this spline configuration and run Nastran in order to get the spline matrix. And then if we look at the time required, we went from more than 2 hours to less than 1 minute. So something like 150 speed up. So it's something incredible. So we really put the attention of this, and everything is needed in order to to keep the solution, to make the solution as fast as possible. Just two applications that I've been working on with two different PhD theses, one with Airbus and the other with the University of Michigan and SCTetra from Rome. So in these two cases in which we studied the nonlinear response of the flap track ferry, and in another one we studied the steady shape of a hail configuration. In both we employ this spline technology. So it was important just to let you see the variety of application that we can have with this technology. Now let's go to the last important aspect of doing eco simulation. So it is the fluid domain deformation. I want to go a little bit more in details about how we handle this aspect. So what we did is, instead of creating something from scratch inside the CFD solver, we thought about we already had. And what we did is that in the interpolation phase of the coupling, the entire CFD domain or the subdomain of it, this depends of the user. A subdomain of the entire domain is transformed into an equivalent linear Nastran model. I'm showing here the same model with got by Tetra and the other one got by Flow, and just to show you the difference in terms of mesh, because Tetra uses tetrahedrons while SC Flow uses polyhedron mesh. So we have some differences, but we can handle both. So I'm not going into details on which Nastran elements we have used, why, and etc., because this is part of the development itself. But the important thing is that by doing it, we have this model put in memory in the HFSI Nastran modules in terms of Nastran matrices, and all the operations to deform, to morph the CFD domain are performed by specific Nastran solution based on Nastran models. So we have a robust solution, an efficient solution, and a fast solution. And another an important functionality that we implemented that I'm so excited about that, because really help and guide the deformation of the CFD domain. It is the sliding option. So what we can do is, for each of the surfaces that we have defined the CFD solver, we can constrain some degrees of freedom or keep free others. So for example, here we have 3 phases, and we have keep free the sliding, the nodes can slide on this direction. So, and this is like in this case, that is the model that I'm going to use for the demo. For this little gap, you can understand how it is going to get negative values, because the gap is really small. So if we allow the node to slide, we really have the mesh, the CFD mesh deformation. So far, we have implemented the sliding option in 3 directions of a rectangular coordinate system. We're working on a cylindrical and spherical coordinate system that will be implemented soon. And the other functionality that we have developed is, in order to help the morphing of the CFD domain, is the possibility to define 2 different zones with 2 different stiffness. So the Eiger stiffness defined by the sides of the element, so the threshold element size, define the zone that is normally, usually that one close to the deformable wall, where we, for example, have boundary layers and we want to keep the shape as it is, and avoid stretching issues or warping, and etc., etc. And we have a different zone, zone 2, in which the elements have a smaller stiffness because they are bigger, they can deform more, and this area is far from the boundary layer, so it is, I would say, less important. And we can do it through the graphic user interface. And just to have an idea on the time taken by this technology to deform the CFD domain is for this model that has something like 45,000 degrees of freedom is almost instantaneous. So everything is shared in memory, so it is really, really fast. Now I want to go to the demo that will be important. And this is the model that I'm going to use. So I have a fluffy duct. It's the same model that I've used in order to show you the technology and the theory behind this coupling. And I am going to show you two different couplings. One is between Tetra and Marc, and the other one in which I used a higher flexible structure with Nastran and SC flow. So two different mesh, tetrahedrons and poly mesh for SC flow, and the Marc and Nastran for the two couplings. So we have pressure-based and density-based solver available. Runs have been used for this simulation, and the time step is fixed for both at 0.0025 seconds, and we have performed 800 iterations, and it takes something like 8 minutes. So 2-3 coupling iterations per second. So it's really fast. And before going through the demo, I want to show you how you want to create boundary conditions in terms of CFD domain morphing. So since I have very little gap between the wall on the bottom and the slab, I want to allow the nodes to move on these pages. So I am I'm constraining only the Y direction. In these other surfaces called lateral free, I am letting nodes widen in X and Y, the constraining in Z. And in terms of these two other surfaces, I am constraining everything. I could change and see what happens. So in this case, in order to reduce the computational times and costs, I only get a portion of the entire CFD domain. So what here is called deformable volume, and I'm going to deform only this portion. So it's up to the user to define which portion of the CFD model is going to be morphed. And for any surface that you define in the CFD model, you can define different boundary condition. So let's start with the demo. So I have prepared two different models. So I call the graphic user interface that we have developed for this general FSI. The first thing is the first page is the file selection, in which we switch from Nastran to Marc and from Tetra to Flow, and we can copy both. We select the files, Nastran or Tetra, and we have some simulation parameters here. So far, Paddle only supports coupling in a front-end simulation, but software can be even used for a static coupling, and we have done it with a competitor that is fluent for an activity with the engineering school ISEA introduced. So we could even, if the CFD solver allows, we can even couple, perform a static coupling with the CFD solver. And so far we have only the explicit coupling. And after we have all the CFD morphing parameters for the volumes, for the boundary condition of the surfaces, and the thickness parameters of the equivalent FEM models that we use today to morph the CFD domain. So, but let's go through the simulation. So I select the Marc model. So this is the Marc model. I select the Tetra 5, and I select here which is the wettest surface from the CFD side. So in this case, flat coupled. These models are available. So in the case you are interested in getting this simulation, we will provide all the models on top of the installation file. So I select the wettest surface, and here is where I select the spline interpolation matrix. So let's get the spline I have already created, so it's really small, and I go to the CFD morphing parameters. So I select phase 1, lateral 3, and up to the 3 surfaces in which I want to put a different constraint, and this is what I have shown you just a few moments ago, that I want to allow the node to slide on the surfaces. Done, and here I put the element, the threshold element side that divides the volume in 2 different areas with 2 different stiffness, and here the ratio of these 2 difference that I have explained you before. Done, and I start the curve simulation between Marc and SCTetra. So I execute, and we are now in the initialization phase in which all the matrices are put in memory. I'm talking about the spline. I'm talking about the stiffness matrices that represent the CFD domain. And here you can see that the Nastran HFSI module started. And this is the interpolation module from Nastran that we have developed to take care of the interpolation between the 2 codes. So you can see how fast is the simulation. So this is the cradle side. Let me show you that Marc is running. So if you look at the SPS, you can see that it's running really, really fast. And interesting is to look at what is happening in terms of CFD deformation. So I can put, you can drop this, something that I really appreciate, that you can drop the results directly on the post processor. So, as you can see here, this is the flap that I modeled, update. So if I put here, let me do something like that in order to show you the mesh on the wettest surface, not like that. Here we are. So this is the wettest surface, and I want also to put the mesh on the plane, so we can see how it is deformed. So automatic selection. So if I zoom in, we can see how the node here has sliding. This is because of the sliding option that we defined with the graphic user interface. And you can see how the flap is moved in terms of displacement. So we're receiving displacement velocity as well for this case. And this is really, really interesting, because if I do something like that, the phase, region, and everything, we can even see what happens in all the surfaces in which we have put different constraints. We can see how the nodes can glide. in this direction, both directions here, and that constraint on the others, and this really helps and guide the CFD deformation. So it is really interesting. So you can, for any surface that you have defined this CFD model, you can define different constraints, so you can really help and avoid as much as we can negative value problems. So for this example, I am pretty okay. I want to switch to the coupling between, so this is the coupling between Marc and SCTetra. So I want to switch to the coupling between, where we are, 208 iteration, to the coupling between Nastran and SC flow, because it is really interesting, because SC flow is the new solution that we have available from Cradle with overset mesh, with a really interesting functionality on it. It's really fast, and it requires very small memory to run. So let's stop this simulation, because I don't want to go through the end. So terminate. Yes, to close it. Yeah, and some others. Okay. So the interpolation module from nothing is still running, because the number of iterations was something like 400. So now I want to go to the coupling between Nastran and SC-flow. So the model is pretty the same. So the model is something that I have already showed you before. Where is it? Sorry. So it is this model on the bottom. So it is exactly the same model with the same subdomain that we have used, the wetted surface. The only difference is that we have used a polyhedral mesh. So we don't have tetrahedral mesh. So we have a polyhedral mesh, and we have to handle it in terms of the coupling. So I select Nastran model. So go to the Nastran folders, and I have used a highly flexible plate in order to show how the polyhedral mesh can deform more than a tetrahedral mesh. I am looking at the SC-flow model, and again I have the flat couple as the wetted surface. I select the spline to connect it and tie the two wetted surfaces. So it is spline skin Nastran SC-flow, if I'm not wrong. And in terms of CFD morphing, I would use the same as before. So we can have some comparison between the two different couplings. So let's constrain phase 1, constrain Z direction for the lateral 3, and the Y direction for up. Done, and the same parameters in terms of threshold element size and stiffness ratio. So let's start the Nastran SC-flow code simulation. So so far we are working on the MPI. So we are working on the MPI for SC-flow. So soon it will be available the MPI, so we can run SC-flow in parallel. So since we're using just one core, in this case will be a little bit less fast than the case in which we use SCTetra, but you can see that it's still running fast. And on top of it, when we use polyhedral mesh, the numbers of degrees of freedoms increases, because with polyhedral mesh we have more phases and more nodes for phases, and so the number of nodes increases a lot. So we, as before, we are in the initialization phase, in which all the matrices are created and put in memory in the HFSI Nastran module, and the two solvers start exchange information soon as the initialization phase is terminated. So the two codes start exchanging information. So if we look at what's happening in terms of this one. I have to go through. Let me go here to post-process results of this program that is running. So let's go and get the results from this simulation. This is really interesting because we can actually with the monitor that is this one, you can even post-process directly the deformation of the main. I didn't do it, so it's not so bad. So let's do something like before. So I am showing the mesh surface region. I will get the couple. That's it. So we can see that we have fully error mesh, and I want to post the plane as well with the meshing. So let's see. Okay, so we have in this case the polygonal mesh that are on the surface. So this is another visualization that is interesting to see the more depth here. And I update the simulation, so we have 34 iteration, and I go here and simulate the information. We can see how the node in this case as well can fly. This is really something like paper, so it's really flexible. And we can see how the lattice surface is moved when deformed, and how the elements follows the deformation, and thanks to these capabilities that is the gliding option, we can reduce we can put away a little bit the problem of having negative glidance. So let's see. So it is really highly flexible this stuff. So I would say that what I noticed so far that if we ever mesh, we can deform more, because thanks to the way the mesh is done, and thanks to the interpolation too that is called HFSI Nastran models allows us to do it in a really fast, robust, and efficient way, and the exchange information between the two solvers. So with that, I would say that the simulation is still running, so everything goes well. So with that, I guess that I am done, and I don't know if I have missed something, but please ask any question and any comments, and I will be happy to provide you with all the information you need for. Just the last thing I want to, since we have developed this tool has been developed from the field, I want to say a big thank you to Laurent Monnier. He's a colleague here in Toulouse who has been working with me on this project, and he's also always so easy to work with me. So, and that's it. So I keep forward to continue with the question and answer, and thank you for the attention and for having joined this webinar.